Everybody, and welcome to our new class about electrostatic deposition. So what we're going to cover today in drug delivery. So if you recall what we learned so far, we learned that on the particle, on the drug that we inhale or deliver in the blood, some forces apply. And this is equal to mass multiplied by acceleration. And we discuss a lot about the gravity force. We discuss about the drug force. We even discuss what does this term mean, changing my velocity. It would not be that easy to change in a sharp turns, right? We're going to talk about the Stoke numbers. But we did not talk about something very, very interesting, which are the electrostatic effect. And that's what we're going to cover today. So before we're going to start, help me understand what's happened to this kid. So his parents did not neglect him. So the kids went down the slider and accumulate electrostatic charge. But we don't see electrostatic charge in day-to-day activities, but only his hair tips, you can see it, become charged. And we can notice it because of the repulsion between the hair. And why this happened only to the hair and we don't see this effect on the body? Of course, also the body have charge. And the reason for that is because the interesting phenomena between area to volume. You see, electrostatic excel when this ratio is very, very low, very, very high. So if we consider the hair thickness, which is approximately 70 microns, we see that this ratio for the hair is huge compared to the body itself. And something very, very similar happened to an aerosol. Look at this. Look at this video. So here are released particles from this jet. And these small particles, small aerosols, also very, very small and short in diameter. And for that reason, electrostatic is very dominant on this aerosol's world. So if we think about it, okay, so why my aerosol would accumulate any charge? And the reason is because of a lot of friction, what's called triboelectricity. You see the inhaler is neutralized, positive and negative charges, but when an inhaler when a particle gets outside of the inhaler, it accumulates its charge. And this phenomenon called triboelectricity. And only then the particle deposit within the human body. So different inhaler have different amount of charge. We can think about nebulizer, single electrons, dry powder inhaler, 200, MDI, meter dose inhaler, 500, and in academic device, we can produce a very, very strong charge, artificial charge. So let's dive into our first question. Let's deduce what is the definition of electrostatic charge. Let's get off some rust. I'm going to be a dead board. So our first question is, as it say on the board, so what is the definition of the electrostatic force? Okay, this is the question. So anybody remember the definition? For me, it's very similar to gravity. What is gravity force? Yeah, but this is a more advanced one. So before that, what I want you to think in mind is we have a property that's sensitive to the field, and we have the field phenomena. So the electrostatic force is very similar to that manner, because what is the electrostatic force? Is something that is sensitive to the field, and we have what? The field itself. And let's do a reminder, what is a field? What produces electrostatic field? Charges. So if I have a positive charge, it emits electric field. And if I have a negative charge, it accumulates, it sucks in the electric field around it. You see it? So this is this E, in a similar way that big masses like Earth produce gravitational field. And what is the formula? What is the formula for electrostatic force, electrostatic field actually? So the formula, if I have some particle number 2, and I apply electric field on particle number 1. So the equation is Coulomb constant, yes, Q2, this is the one that produces the electric field, divided by the distance squared. You see it? And this is the distance between 1 and 2, of course, okay? Just a reminder, Q, it's 9 to the power 9. It's a very big number, Coulomb Coulomb constant, and it can be also introduced as 1 over 4 pi epsilon. Okay? And epsilon is a very small number. You see, it's 1 over the other. It's 8.85, 10 to the minus 12 farad per meter. Yes? And if you want to write it as a vector, you see here, let's do Al. So if you want to write it properly as a vector, so this is the scalar, right? And in the denominator, we're going to write the vector of the location of particle 1, the one I want to introduce the field, minus the location of the one that produced the electrostatic field, right? And this is to the third. And for the direction, I'm going to do it here, sorry for that. For the direction, it's the same value. So you need to calculate it one time to the magnitude to the third and multiply by that. Okay? So this is the electric field. And if you're going to push that one inside, we finally have our electrostatic force. So the electrostatic force is equal to K, Q1, let's do it like this, K, Q1, which is the same Q from here, and from the electric field, you have this thing, right? Yeah, let's do it with this direction. You see? The red is the electric field, the blue is the particle itself. Okay, now when we know the force, we see something very, very interesting. What is the phenomena of space? The dominant, the equation, the distance between the particle. So right now, this was section A, right? Just a reminder, what is the electrostatic force? And in section B, I want to give you a problem. I go to the board. So we have a given inhaler, some inhaler, and this inhaler produces high concentration of particles. How many? Millions of millions, exactly, 10 to the power 12. Millions of millions particles per cubic meter. This is how dense the particle. And what I ask you, what is the average distance between two particles? Why we want to find the distance? Because we know it's very important for the electrostatic force. Let's go back to the board. So B, I give us the concentration of particle is 10 to the 12 particles per meter cube. That means that if I'm gonna count my particles, it's gonna look something like that, yeah? I have these particles, a lot of particles. How many? 10 to the 12, right? And they are confined in some volume. That's the reason I can count them. It's not all the particles that I have. So if I'm gonna take one, this is 1 meter, this is 1 meter, right? So this is the concentration. How many particles do I got inside? And my question to you is, if I have these particles, let's draw also some outside of the box. This is our particles, right? So what is this distance? Okay, let's call it delta x. Okay? What is this distance equal to? We try to find what is delta x. The average distance between adjacent particles. And the way to find the solution is very cool, because you see, there's two ways to write the concentration. You can use a lot of particles in a very big box. This is the concentration. But you can do the other way around. You can count only one particle. You see Cp equal to only one particle divided by this volume until I reach to other particles. You see it? To this volume. And this volume is a delta x, right? Delta x. It's actually delta x cube, right? Distance between the particles. So I can present, I think about that the big way, right? And this is what? The small way, the gentle way how to see concentration, okay? So I can compare the two of them, and I'm going to get that Cp equal to 2x to the minus third. You see it? That's exactly what we got, right? So actually delta x is Cp to the minus third. And if we're going to apply here 10 millions of millions, right? Minus 3, this is actually equal to 100 microns. So if you have that amount of concentration, the average distance between particles is approximately 100 microns. And this is relevant where? To the electrostatic force between them, you see? Going back to the TV, so after we find out, it's working? Opa. Okay. Okay. So after we find out this effect, so we want to talk about the electrostatic repulsion between these aerosols. So why they would repel? Think about it that from inhaler, the particle being introduced by the same manners, right? Just calculate it. If you calculate it, 10 to the 12 to the minus third, it's going to be 100 micrometer. Okay? Perfect. So if I'm going to introduce particles in proximity, they want to extend, they want to repel each other, right? So this is our next question. We have some particle with the charge Q equal NE. Okay, I'm going to remind you, N is it's a natural number, counts, and E is the charge that electron has. Okay, and I want to ask, what is the electrostatic force of repulsion? So back to the board. Okay, so we're interested in find out what is Fe in our case, right? We know that Fe in magnitude is approximately, you know, the distance between the aerosols. Let's do it equal. R squared K Q 1 Q2. This is the general idea. And we can say that the aerosols have charge Ne, all of them, in the same similar charge because they've been exhaled from the inhaler in the same manner. They accumulate the same amount of charge. So we actually have the same charge, right? KQ squared between them. And just to remind you that E equal to 1.6 times to the minus 19 coulombs, okay? And the distance between them can be approximately R delta X, right? It's not true to all the particle, you know, the jiggling around, but on average, this is approximately the force, right? And we know this one to be KQ squared. This is CP, right? CP, the particle concentrations, to the minus third squared, right? So if you're going to organize our equation, the repulsive force between the particle, it's actually K, NE, I put Q as NE, right? NE, C to the third square in the X direction. So this is the repulsive force between the particles. And this is a very interesting force. So this force is actually make the cloud of aerosols try to spread around. But what is more important? To spread around? Okay, maybe this effect is happen very fast, or maybe the gravitational sedimentation make the particle fall much faster than the cloud even start to spend, or maybe diffusion is jiggling around much more faster, right? So for that, I'm going to that board for the last section of this question, which is asking the question, who is governing this equation? So we see here that we have the electrostatic force. Let's write it down here. So we have here K, right, Coulomb constant, very big number, don't forget. And we have the charge of the particle, very small number, don't forget, right? Very small number, don't forget. N, E, Cp to the third squared, right, in the X direction, let's say. And we want to evaluate who is going to win, right, in the equation. Look at the TV. So we have, maybe it's gravitational, maybe it's the impaction, maybe it's the electrostatic. So we want to figure out. So we can go back to the lung, yes, and say, I can tell what is the lung in a very simplified way. I can say the lung is just the tubes. Here I have a tube. And the size of the tube is the diameter, right? It's exactly the diameter. Each tube has a diameter. And the length is approximately a diameter, right? 3 times the diameter, 2 times the diameter, each branch, right? The velocity inside each tube, I know it. I know the flow rate in the lungs. So I can evaluate that the flow rate, right? That the average velocity is the flow rate divided by A, and A is pi d squared over 4, right? So I can tell what is the average velocity, right? I can say that U, is approximately some U average multiplied by non-dimensional U, which gives us the direction, right? So we know how the velocity behave, we know how the distances behave, and we also know if there's a particles here, how much time on average it would stay inside the tube, right? How we can know it? We know the time, right? And we know the distance I want to go, d, the diameter or the length, right? And divided by the average velocity. So we actually know kind of a time, characteristic time. So if we plug everything in, okay, so to this equation, Newton's second law, and just to remind us, the people that don't remember it, so m is the density of the particle multiplied by the volume, and the one that don't remember, B here is, let's write it here, B is the mechanical mobility, it's cc over mu of the fluid, 3 pi diameter of the particle, right? And maybe correction factor for the shape and stuff like that. So if we're going to plug all this non-dimensional number inside our equation, we're going to get new equation, and we talked about it. mg would become h, right? Let's write it here. Become h, right? It's going to be, it's going to be h at the gravity direction, yes? And we can also say that gravity is some constant in the direction of gravity, right? We're going to get h, and h is just tau g, the terminal velocity, divided by the average velocity in the airway, right? How much time it takes me to fall, how much time I spend inside. Makes sense? We have the electrostatic effect, right? So the electrostatic effect of how much particle expand in space called the space effect, SPC. And this is the, we can say the radial direction, right? Just go outside, right? So this one, and it's look like this. It's the mechanical mobility, K divided by U, equal, multiplied by NECP to the third squared. Got it? Yes? So we can understand how dominant is this force. The question? Huh? Yeah, U, of course. All the U, I said all the velocity of the particles are approximately the average velocity. Just to see who is win over the other, this is equal to what? I have another color? Yes, the Stock number, right? And the Stock number tell you how dominant is the change in velocity. I forgot here to put UREL. UREL, which is a non-dimensional velocity. This is equal to 1 actually. And here we have Stock. Stock tell us how dominant is the acceleration. If particle can accelerate and change its direction, this is dominant, right? Okay, so maybe it's not going to succeed to do it. That's what happens when Stock is very big. So Stock is equal to the stopping distance, tau multiplied by U0, U average, divided by D. Perfect. So this is non-dimensional Newton's second law equation for a particle under electrostatic effect of repulsion, gravity, and changing the velocity, right? So what's really interesting us, it's what? No, this is the real D. No. T, yeah, T is a non-dimensional. Very good. Thank you. Very good. This is, yeah, okay, perfect. Everything is clear so far? So what's really interests us is to know who is dominant over the other, right? So what we really cared about, I'm going to write it over here. So what's our really interest is about talking what is the ratio between these non-dimensional numbers, right? We want to know what is the difference when somebody is much larger than the other. So for example, let's compare, I don't know, let's compare space number, yes, versus Stokes number, and versus h. You know what? Let's start with h. Let's see what is the scenario that the repulsion of particle because of electrostatic force versus gravity taking over. So h is pretty straightforward. It's tau g, the terminal velocity, divided by u, and b up here, q divided by u, and e, write it, and e cp to the third squared, right? That's what we have. Okay? So first I see something very, very interesting when I compare them. The velocity canceled. Because think about it, electrostatic gravity need time to fall, right? So if you breathe really fast, I don't have time to fall. If you breathe very slow, you have time to make this free fall. The same thing electrostatic. Electrostatic want this repulsion to happen, but if you breathe really fast, you did not succeed to do it in the tube. You see it in the airway. Got it? So we see that in the ratio, it doesn't matter how fast you breathe. Because if you breathe really slow, it's going to help two of them. And if you're going to breathe very fast, it's going to make the life hard for both of them. Makes sense. Another thing that is very interesting that I immediately see, I see this. B and tau. B and tau, just to remind you, the definition of B over tau is actually 1 over the mass. Okay? 1 over the mass is just to remind you that this is proportional to the diameter to the third. Which means if you have the big particles, space would not work, right? If you have a very small particle, no gravity. Makes sense, right? 1 over, perfect. Here we have G, right? And now we got the dummiest thing ever. What did we got? We got below mg, right? mg, and above we got k and e cp to the third, which is the electrostatic force. We just got our non-dimensional is to compare the two forces. Makes sense, right? Something that I want you to already see, which is very important, is that what's happened to cp when it's entered to the lung? This is generation 0. Okay? So what is the role of the lung? The lung expand, right? So the lung expand, right? So what actually happened is that you have some V here, you have some particles, but suddenly when you go to the next generation, V1, suddenly you have more volume, okay? So Cp, just to remind you, is a function of number of particles per meter squared. So this increase when you go deep into the lungs. You see it? So here I have even more volume, right? This part, V2, right? You see it? And also, what happened to the particles as I proceed? I lose them. Some of them would not survive to continue, right? So this goes down, right? So Cp goes down double. So what's happened? Space is becoming weaker and weaker and weaker because it loses concentration. While the gravity is constant all the time. It doesn't change. I would put a small disclaimer that we're going to talk about that the diameter of a particle maybe can change along the way, okay, because of the relative humidity, okay? But if you're going to compare the rates between these two, you can know who is win over the other. Yes, it's clear? Perfect. Let's compare space to Stokes number. Question, yes?
The overall volume, I guess it goes up, but...
It goes down, it goes up, yeah.
But the diameter goes smaller and smaller.
That's true. He said something very important. He said, Ron, the diameter is becoming smaller and smaller and smaller. But the diameter is not going smaller faster than the exponential growth of the number of generations. Okay? I agree that the volume of the alveoli, for example, is very, very small. Few hundred micrometers. But most of the lungs is the alveoli. Okay? Most of the volume of the lungs. Perfect. Good. So now let's compare space to space effect versus stock number. I remind you, stock number is I want to go that way, nobody gonna stop me, inertia. And suddenly the flow want to take a sharp turn. Who said that I want to do the same thing, okay? So this is the inertia. So space is the same, right? It's B, K, N, E, C, P to the third square U. Stock, on the other end, is the stopping distance, right? It's the U average, I don't want to write so much, divided by the diameter. And we see something very interesting. This is not canceling out, right? This is becoming U squared. You see it? So velocity is very important to say if space would win over stock, or impaction, stock would win over space. You breathe fast, fuck you, space charge, right? You breathe slow, fuck you, stock. That's what actually happened. We see again this thing, B over tau, which is 1 over m. And this is similar to kinetic energy, you see it? We have below kinetic energy, mu squared, you see? Okay? And this again say that if you go with the small particles, space will take over, okay? Great, and again we have the diameter. I'm going to put the diameter here, and this is very interesting. This is kind of asking, where are you in the lung? You in a big diameter? You in the initial place where the velocity is very high? Or you very, very deep, where this is very small and this is very, very small, right? So this ratio is actually the GPS, telling you, tell me where you are, and I'm going to tell you the ratio between them, you see? Perfect, and then we have all the electrostatic features, right? NE, the concentration, how much charge we put on it, perfect. So we learn about this comparison, which is very important for your homework. This comparison, perfect. What we forgot to compare, which mechanism? What? We forget one, it was not in the equations. We learned in the last time, the fusion. We can compare space to diffusion, right? So let's compare space. And what is the non-dimensional that depict diffusion? Remember it? It was the inverse Paclet, okay? And you're also going to see it in the lecture with the fluid flow, okay? With the air. So the inverse Paclet is said the constant of diffusion, not to be confused with the diameter. It's a different value, right? If you don't remember, the diffusion coefficient is the mechanical mobility multiplied by the thermal effect, right? Boltzmann constant and the temperature. And here below, we have U multiplied by D. See? And we see something very interesting. We again see that what happened to the velocity? I don't care, right? They don't care about the velocity at all. It's because both of them enjoy the velocity. We see here something very, very cool. We don't care about the shape of the particle and the size of the particle and the flow that the particle within, because the mechanical mobility canceled out. You see it? Okay? Because inside B, going here, just to remind you, B from the drag force, all these phenomena is here. This is size, size, flow, maybe correction shape, right? We have the X. So they don't play. Why? Because if I'm a small particle, I enjoy diffusion. If I'm a small particle, I enjoy space effect. If the flow is not viscous, the electrostatic enjoy it, easy to expand. If the flow is not viscous, the diffusion, the effect of temperature, it's very easier to jingling around, right? So no surprise, but cool, yes? And we also see that D is go up. right? You see it? So this is the ratio between electrostatic and Paclet, inverse Paclet, diffusion. Got it? Very important, very important, very important. Got it? And I want you to see that what's happened with the location in the lungs. Yeah. Yeah, squared. Yes, thank you. Okay? So what happened in the lungs? If you have a very small length scales, for example, the acinal, CP would not survive, you agree with me? And this is very small, which means diffusion win. But if you are in the upper airway, right, very fast, CP is very strong, who would win? Space, okay? So if you're thinking about your drug delivery, you can understand that charge can help you in the upper airway more than diffusion. You see it? Okay, great. So I go back to the TV. So we did a very cool summary, and I want to finish the first hour that we have with some papers and also cool video. Okay, so first of all, this paper, I love it. It's a computational fluid dynamics. They took a small particle, and they exposed it to the upper airway. You see it? Actually, yeah, pretty disgusting, but I have the upper airway, a real one over here. I'm going to show you later. So they expose the upper airway. Yeah, they expose, we have the real deal here, guys, okay? So they expose it, and I want you to see what's happened when they increase the charge. What happened? You have more deposition. More particles stay in their computational model. You see it? Okay? And if you're gonna see it, they took this model, you see? The big airway, the trachea and the bronchus, and they expose it to different amount of charge, but also different amount of sizes. We talk about it, how size plays significant role in deposition. So you see, I'm gonna, clean, and I'm gonna show you only 0 versus thousands, okay? So you can see the big difference. So you see for the small particles, wow, this is a major change in deposition. But for the big particle, 2.5 micron, it doubled the effect of deposition. You see it? And the reason it's an additive mechanism, and also not only in a computational, we did it experimentally. So you see, this is Muhammad Ali. I don't know if this is the same guy. Maybe he has 60 years crisis and he wants to do electrostatic in the lungs. But he did an in vitro study. He exposed 30 liters per minute with different sizes, and he saw that because of electrostatic, he had 3 more times the deposition in the upper airway. Okay, so this is dramatic effect. Okay. But I want to show you something very cool, very, very cool. Okay, so I teaching you, general deposition. Okay, it can be in the drug delivery, but it also can be in the industry. Electrostatic plays significant role in filtering air and also in painting. So they charge the air source, but they also charge the rail. And this is very efficient in painting and also in air pollution. It doesn't, because particle deposit. Here it's a normalized nebulizer, you see, spray on one side of the apple, but look what's happened with the electrostatic. It's painting the other side. How crazy, why this is happening? Look, this is without, and this is with. How crazy is this, okay? So after the break, okay, we're gonna talk why this is happening, okay? Okay, great. If you have any questions, see you at 11:15.